presenting microclimate regulation and urban trees, the relative effects of radiation and transpiration on canopy temperature and pedestrian thermal stress.
Okay, thank you, Scott, and thank you everyone for coming. And I would like to thank my collaborators, Francesca Ugolini from the National Research Council in Italy, and Pedro Berliner from Ben-Gurion University in Israel. And I'm going to be talking about a study that we did on how urban trees regulate microclimate, and looking particularly at the effects of radiation and transpiration from urban trees. So we all know that our cities are getting hotter due to both local and global effects, and we know that one of the best strategies we have at our disposal is what we call urban green infrastructure, particularly urban trees. But trees need water, and many of our cities are not only becoming hotter, but they're also becoming drier. So this means that in many locations, water is scarce, and we don't necessarily have a lush canopy cover. And so in a situation like this, which is in Israel, we can ask the question, can individual trees actually make the city cooler? Or can they make the city more comfortable for pedestrians under hot conditions? And the first answer I would give is yes. You see here, as Luciano was pointing out, we can get enormous temperature reductions on the ground, the radiative temperatures of the ground surface. But we've checked many times and found that in a situation like this, the effect on air temperature is negligible. Because the urban canopy layer, the air is well mixed, have circulation, and it'll be difficult to even find a difference in air temperature between here under the tree on the sidewalk and here in the middle of the street. Also notice, though, the temperature of the underside of the tree canopy is also very low. So if we're talking about shade trees, what would happen if we talk about artificial shade trees, about artificial shade, which don't need any irrigation at all? And so this is an experiment from several years back that we did with Limo Shachuabar. And this was in two courtyards, one with a series of trees and one with an artificial shading mesh. And in terms of shading, they were essentially equivalent, both blocking out about 75% of the solar radiation. On the other hand, the tree canopy operates entirely differently from a shading mesh. You can see the surface temperature, the radiative surface temperature of the underside of the tree canopy and of this shading mesh. And many of you might be thinking, well, that's obvious. I know why that is. This is a tree. This is a living organism. But before we jump to how obvious the answer might be, I just want to remind everyone about what's going on and what influence shade trees can have on the microclimate that's experienced by pedestrians. Of course, we have shortwave radiation, but not just direct radiation, also diffuse and reflected. We, of course, have long-wave radiation emitted from the surroundings, including the tree canopy. We have convection that's dependent on both wind speed and air temperature, and also humidity, which limits evaporative cooling of the body. And the question we might ask is, to what extent the thermal environment that we experience is affected by transpiration, that is, the evaporation of water from the leaves of trees, from the canopy. I'm going to steal a quote here from the chair of our session in a very nice paper that's very recent from this year, because there's a lot that we do already know about this. And this summary says, although the impact of trees on long-wave radiation and wind will tend to increase heat exposure, the reduction of heat exposure caused by shading and transpiration typically dominate during daytime, resulting in a strong cooling effect on trees. So with the emphasis on shading and transpiration. The question we're asking in this study is, what are the relative contributions of those two things? How much do we get from shading and how much do we get from transpiration if we are a pedestrian standing under a tree canopy? Now, we started to sort of attack this problem in a pilot study some years back with some trees in a nursery, camellia, in which we measured the surface temperatures of two trees, one of which was transpiring normally, and one which we're trying to imitate a non-transpiring tree by spraying on it an anti-transparent coating on the leaves, which strongly restricts the transpiration of the tree, not necessarily healthy for the tree. What we found, at the top of the tree canopy, very significant differences in leaf temperature and surface temperature, but at the bottom of the canopy, much, much smaller differences. So this gave us an indication of something going on, but we didn't know exactly how much the non-transpiring tree was really non-transpiring. It wasn't an urban setting. So we decided to do a more detailed and in-depth experiment, and this is in the arid Negev desert in Israel. This is in a courtyard of a building at our research campus of Ben-Gurion University. We took several individual trees. I'm going to be focusing just on these two here. The English name of this is the Chinese flame tree. They're both planted in large containers. I'll tell you why in a moment, but mainly so that we could control irrigation, the substrate, all of the growing conditions, and so these two individuals would be as similar to each other as possible. And after a period of acclimation, instead of spraying anti-transparent, we simply cut off the water supply to one of these trees. So during the main observation period, we have one individual which is transpiring normally and another which is subjected to an induced state of gradually increasing water stress. Very important was to measure the radiant surface temperature of the tree canopy at different points, and we used 3 different techniques to do this. So real quickly, the first was attaching thermocouples to individual leaves and shielding the thermocouple so that would be in direct contact with the leaf and not exposed to the environment. The second was using thermal imaging with a FLIR 5 minutes, a thermal imaging camera, and this gives us spatial extent, although not temporal continuity, and also using radiometers to actually measure the long-wave radiation downwelling from the tree canopy. And just real quickly, the 3 measurement techniques, a comparison, you can see that they all produced very similar results. I'm going to be showing you results of the thermocouples. Before I do that, though, it's very important that we do know that one of our trees is transpiring and one is not. And so what we did was we essentially custom-built lysimeters. We used digital scales to weigh the pots with the plants, with the change in weight representing the transpiration, and so that it didn't represent anything else. We used a mulch to prevent surface evaporation, and we collected the drainage water and measured that and took it into consideration. And so we find that from the time that the water was cut off, our transpiring tree is transpiring normally, and without irrigation, the transpiration from the second tree is going down to a negligible level. So how does this affect leaf temperature? First, we're going to take a look at the top of the tree canopy here, and we're going to see that from this point right here, when the irrigation was cut off, the temperature at the top of the tree canopy was essentially identical, and then a gap grew between them over 4 or 5 days. So at the top of the tree canopy, transpiration is certainly having an effect up to 6 degrees. But at the bottom of the tree canopy, this hardly happened at all. The difference between the two is less than a degree. So in fact, cooling is negligible at the bottom of the tree canopy. That's what we have above our heads. Why is this so? What we did to get a more in-depth picture is we actually measured individual leaf transpiration at different points with a Light-Core portable photosynthesis system. And what we found is that at the beginning of the experiment, when both were irrigated, the transpiration at the top, the top leaves was essentially identical. The transpiration stayed constant for the transpiring tree, but as expected, declined drastically without irrigation. At the bottom of the tree, we find something different. We find that the bottom leaves are not transpiring or transpiring at a very, very low rate to begin with, and therefore the difference in transpiration is statistically non-significant. So to wrap up, we can say, or we can interpret these findings to mean that the temperature of the underside of the tree canopy is mainly regulated by the cumulative shading effects of multiple layers of leaves, and to much lesser extent on leaf transpiration. And why is this even important? Why are we interested in trees that don't transpire? Because drought-resistant tree species in arid regions might not be transpiring much, but can be very, very valuable for improving the microclimate. And we might be able to say the same thing about artificial shading devices, provided that they're designed to minimize the re-radiation of absorbed solar energy, for instance, by using leaf-like elements, artificial trees, and just a random sampling. I want to just sum up and say that I would suggest that we think about not just urban green infrastructure, but urban shade infrastructure, which is vital for our cities in the future. There's no one solution. There's an ecosystem of solutions. And before I finish, I would like to acknowledge our colleague, Dr. Limor Shashua-Bar, who very sadly passed away just several months ago. And I think that many of you might know her through her publications, which are widely cited in this field, and who's passionate about urban trees. And I always have to make a pitch for the Urban Climate newsletter, which you're all welcome to submit articles to anytime. And thank you very much.